Hi, this is Qiaochu at Lehigh University. In this video, we're going to talk about the homework for week 12. Let's take a look at the first one. There is a 13.1 feet wide rectangular channel, conveys 72.7 cubic feet per second. We need to determine the depth of water that would be produced upstream of a 3.28 feet high weir that is built across the floor of the channel. We also need to determine the velocity of flow over the weir, and we assume the weir friction loss and the velocity head upstream are negligible. Now let's solve the problem. From the figure on the right-hand side, we know that the upstream is subcritical and the flow approach to supercritical after passing through the critical depth at the top of the weir, which means that the water depth on the top of the weir is the critical depth. So to solve the first problem, the velocity of flow over weir, we need to calculate the critical depth first. Based on the equation 6.14, we can calculate the critical depth because we know the flow rate is 72.7 cubic feet per second, and we also know the width of the channel is 13.1 feet. So we can get the critical depth is equals to 0.985 feet. Then, because the velocity equals to Q divided by the area, we know that for the rectangular channel, the area should equals to the width of the channel plus times the critical depth. Then we can get the velocity over weir, it equals to 5.63 feet per second. Next, we can calculate the depth of water by writing down the energy equation at these two sections. Because it is a frictionless weir, the energy upstream should equals to the total energy downstream. At the upstream, the elevation plus the water head plus the velocity head should equals to the height of the weir plus the critical depth plus the velocity head. Based on our assumption, the velocity head at the upstream is equals to 0, and we also know that the elevation at the upstream is also equal to 0. And we know the height of the weir is 3.28 feet. And we just calculate the critical depth and the velocity over the weir. After we bring this value into the energy equation, we can get the depth of water. At the upstream, it equals to 4.76 feet. Let's move on to the second problem. There is a rectangular channel, and the energy gray line upstream of a weir, which is capital H, is 2.6 meters above the channel bottom. The weir is 1.4 meters high and 5 meters wide. The flow rate is equals to 10 cubic meters per second. We need to determine first the actual coefficient of discharge, C sub D, considering the energy losses. And then we need to determine the amount of energy loss in meters. Now let's solve the first problem, the actual coefficient of discharge. Based on the equation 8.8, we know that for a frictionless weir, the discharge for a unit width of the channel, it equals to 1.7 times h sub s to the power of 1.5. The 1.7 here is the stated discharge coefficient, and h sub s is a vertical distance from the top of the weir to the upstream water level. So the h sub s is equals to h minus x. Because this equation is used for frictionless weir, but in this problem we need to considering the energy losses. Therefore, we need to recalculate the discharge coefficient. Based on the equation 8.8, we can write down the equation. The Q is equals to the coefficient times the vertical distance from the top of the weir to the upstream water level. And the Q is equals to the capital Q divided by the width of the channel. It equals to 2 meters squared per second. And the h sub s is equals to the capital H minus the height of the weir. It equals to 1.2 meter. Then we can get the actual coefficient of discharge, C sub d, is equals to 1.52. Then we can calculate the amount of energy loss by applying the energy equation at upstream and weir. At the upstream, the total energy is equals to the elevation of the channel plus the water depth at upstream plus the velocity head. It should equals to the height of the weir plus the critical depth, which is also the water depth on the top of the weir plus the velocity head and the head loss. Based on our assumption, the velocity head upstream and the elevation of the channel is equals to 0. And based on the given information, we know that the water depth at the upstream is equals to 2.6 meter, and the height of water is equals to 1.4 meter. And for a critical flow, we know that its specific energy is equals to 1.5 times the critical depth based on the equation 6.8. And we can calculate the critical depth by applying the equation 6.14. Then we can get the head loss. It equals to 0.087 meter. Now let's move on to the third problem. In this problem, we know the designed flow rate is 935 cubic feet per second. The static head is 4.2 feet. The spillway coefficient is 3.5. We need to determine if the design can be accomplished if the spillway width is limited by site conditions to roughly 30 feet. If not, we need to suggest some alternatives that would meet the existing design conditions. First, we need to do the feasibility check. By applying the equation 8.9, ignoring the approach velocity, we can calculate the flow rate. Because in this equation, we know the spillway coefficient is equals to 3.5. The spillway width is 30 feet. The static head is 4.2 feet. Then we can get the flow rate. It equals to 904 cubic feet per second. By comparing with the design flow rate, the flow rate we just calculated is smaller than the designed flow rate. Then we know that the design flow rate cannot be met under these conditions. Then in the next step, we need to change the site conditions to meet the designed requirement of the flow rate. Based on this equation, we can change the spillway coefficient. The width of the spill width or the static head. For instance, if we change the spillway width, also based on the same equation, we know the design flow rate is equals to 935 cubic feet per second, and the spillway coefficient is 3.5. The static head is 4.2 feet. Then we can calculate the revised length spill width is 31 feet. Or we can change the spillway coefficient. In this situation, the flow rate is a design flow rate, and the spillway width is 30 feet. The static head is 4.2 feet. Then we can get the revised spillway coefficient is 3.62. Therefore, to satisfy the design flow rate, we can slightly increase the spillway width, or we can increase the spillway coefficient. Now let's take a look at the last problem. We need to describe how water quality changes occur during each phase of the hydrologic cycle. In other words, we need to describe how the particles, salts, minerals, nutrients, or pollutant changes in different phases of the hydrologic cycle. For instance, in clouds, the water droplets condense around dust, salt particles, or other human sources. For the precipitation, the droplets pick up air pollutants and other natural occurring particulates. For interception, depression, storage, the water pick up natural and anthropogenic pollutants existing on plants and ground surface. For the evaporation, the salts minerals are left behind. And for the infiltration, the water dissolves and transports salts, minerals, and nutrients in the soil. For transpiration, nutrients are transported into plants from the water existing in the soil. For aquifer, water can dissolve or transport many of the minerals or pollutant it encounters. For the surface runoff, the water transports many surface minerals, organics, and anthropogenic pollutants. For lakes, oceans, or rivers, the natural or anthropogenic pollutants are received, stored, and transported.